Here's what we need to do today. Definition. Of polar coordinates. Relationship to rectangular coordinates. And converting, well, I'm actually going to write it this way. We're going to go in both directions. To and from polar and rectangular coordinates. Right. This is not difficult stuff. It really isn't, but it is new. Brand new. You've never, most of you, I would assume, have never been introduced to this. So it may seem like it's difficult. It isn't. It's just new. So be patient. Okay? Make sure you do the homework and not just copy down the answers like a lot of you have started doing. Not good practice. Not good practice. And then you wonder, oh man, I just didn't do well on this test. I wonder why that is. I could tell you. If you want to come up and have a discussion with me, I could tell you. But anyway, here's what you're used to. Draw this. Oh boy, that sucks. Draw this. Oh, that's even worse. My lines are not straight today. We have the x-axis, we have the y-axis. This is what's called a rectangular coordinate system. This is what you're used to using. This is what you've been using since junior high days. To locate a point on the plane, you've been using what's called the rectangular coordinate system. And it's called rectangular because to locate a point, it has a horizontal component and a vertical component. Yes? That's why it's called rectangular. It has those two components. For example, this point right here, how would you describe the location of this point on a rectangular coordinate system? 2, 2. And that works pretty well. Rectangular coordinate system is great. It's especially great for functions, for graphs that are functions, meaning it passes the vertical line test. Quite often with graphs that aren't functions, like circles, ellipses, the hyperbolas that we saw. And then you'll see some other graphs that are really strange that aren't functions. Quite often it's easier to describe those functions or those equations using a different coordinate system called the polar coordinate system. So here we go. Oh, this is also referred to as the Cartesian plane, named after the mathematician René Descartes. His first name was René. He was Swiss. That's how they do things over there, I guess. The polar coordinate. You guys never heard that story about how he came up with this? I told you the story in this class, didn't I?
Please tell.
I told you. You haven't heard it? You guys are lying sacks of crap.
I swear.
Well, little René was sitting in bed, probably sulking about his first name. I don't know. But he was lying in bed, looking up at the ceiling. This is a true story, actually. I'm not making this up. He was looking at the ceiling. He saw a fly on the ceiling. And he was trying to imagine how he would describe the location of that fly on the ceiling if somebody were to ask him, hey, where's that fly? So he broke his ceiling up into quadrants, This is a true story. He broke his ceiling up into quadrants so he could better describe the exact location of the fly on the ceiling. And that's where we have the 4-quadrant rectangular coordinate system. So it was a pretty big deal. It was a pretty big geometry break. His mom came up and said, "Hey, where's that fly?" "It's 2 units over and 3 units up. Can I go to bed?" So anyway, in a polar coordinate system, you have a horizontal ray like this. This is what's referred to as the polar axis. This itself is called the pole. So you have a pole, you have a polar axis. It's always horizontal, pointing to the right.
Yeah.
And then any point on the plane of the polar axis is described so. Let's put a point out here. Point P. The location of this point is not described using vertical and horizontal components because we don't have a vertical and a horizontal axis here. The location of this point is described by the distance from the pole, that's called R, and the angle that distance segment makes with the polar axis. That's how you describe the location of a point on the polar axis. So R is a distance from the pole. Theta is the angle from the polar axis. Yeah.
Is that angle always going to be in radians?
It doesn't have to be, no. That's a good question. Could be in radians or degrees. Yep. Now, to help plot your points better, at least on a test, I'll provide you, let me see if I can grab a picture of this real quick. Give me 1 second. This is generally how you're going to see a polar axis on your test. This is generally how you're going to see a polar coordinate system on a test. Okay? Kind of. So yeah.
It looks like a target.
Just make a quick sketch. Draw a vertical and horizontal line here, and then this is 30 degrees, this is 45 degrees, this is 60 degrees.
So it is unit circles, what you're saying.
In a way, and you'll see why this is so helpful here in a second. But just take a second, and as best you can reproduce this picture on the website, on our class website. I'm going to post this that you can print off. Let me show you here real quick. This graph paper that you can use, because there's going to be a little bit of graphing. So it'd be best if you just print this off and do your graphs on here.
I feel like Gabe's struggling with this concept.
This really does make graphing in polar plane so much easier. Because everything is about a distance from the axis and an angle from the axis. Or a distance from the pole and an angle from the axis. So here's example 1. We're going to plot a few points. For part A, let's plot the point 3, 3 pi fourths. 3, 3 pi fourths. Now here's the reason for all the circles, you guys. You think, well, those circles just mess things up, but they really don't. What does the number 3 represent? It means it needs to be 3 units away from the pole. So if you go to the third circle out, no matter where the point is around that third circle, isn't it 3 units away from the pole? That's why that circle is there. Because you can put a point anywhere on this third circle and you're 3 units away from the pole. Now, where exactly on this third circle do I want that point to be? Oh, no! What?
What did you do?
Hold on a minute. If I erase those points, I erase the picture. Facing a dilemma.
To highlight everything and then tell it no.
Hold on. Dang it.
Why didn't you just go and make the picture lock? How do you do that?
I know. I have to try this again. And lock. Okay, so we're on the third circle out. Where is 3/4? Alrighty. So this is the point A. The distance from this point to the pole is a distance of 3 units. And the angle measured from the polar axis to that segment connecting the point to the pole, that would be an angle measure of 3/4. Let's do this one. 2, negative pi 6. Now these angle measures happen to be in radians. It doesn't have to be in radians. They also could be in degrees, but we're sticking here with radians. So if the first number is a 2, that means we're going to the second circle out, because that's 2 units away. Negative pi 6 is right here, going in the negative direction. So this would be point B. Now, this next part, write this down carefully and really think about what you're writing. And don't just, with half of your brain, write this down, and with the other half of your brain, worry about what you're going to text in the next 5 seconds. So, R can also, well, now what does R represent again? Before I finish this statement, what does R represent? A distance from the pole. Remember that. R can also be negative. What? R can also be negative. If that's the case, add 180 degrees to the angle. What's that? That's why we add 180 degrees to the angle and consider that to be a positive distance. So for example, let's keep it in on example 1, but let's do part C. So for part C, let's talk about the point -2, pi/4. -2, pi/4. Here R is negative. So according to what we've written here, we're going to add 180 degrees to the angle. So pi/4, let me see, isn't this line right here the pi/4 line? So that's pi/4 right there. If we add 180 degrees onto that, where are we going to be? Just on the opposite side. Okay, so we're still going to be the second circle out, but instead of pi/4 here, we're going to add 180 degrees, and that's going to be this line right here. So the point is going to be the second circle out down here. This is point C. Yeah.
So does that mean R is like the distance going to the right? Because like if it was 2 to the right, like positive 2, then you go out to the right 2, or like 2 circles off the right, and then you'd go pi fourth. It's negative, then you're going negative 2 to the left, and then you're going pi fourths from there.
I see what you're saying. You can think about it like that, and that'll be true. The thing you have to be careful of, though, with this kind of a coordinate system, there isn't really the rectangular coordinates like you're used to, like this is the positive direction, that's the negative, you know what I mean? But what you're saying, I can see what you're saying, and I can see it like that, yeah. It's not totally incorrect. But that's how you plot points in the polar coordinate system. Now let's go back up. If you wrote this, let's take a look at this in your notes again, this rectangular coordinate system. How would we describe this same point that's on the rectangular coordinate system? How would we describe its point if this were a polar coordinate system? It wouldn't be 2, 2 anymore. How would we describe the location of that point? Pi fourths. I agree with you there. It is, if we imagined a line coming here, wouldn't that be a 45-degree angle? So we could describe the same point using an angle of pi fourths. But what's the distance? It'd be slightly more than 2. How would we find the distance? Pythagorean theorem. If we have a horizontal distance of 2 and a vertical distance of 2, what's the length of that hypotenuse of the right triangle? 2 squared root of 2. So this same exact point has a location 2, 2 on the rectangular coordinate system, but on the polar coordinate system it's 2 squared root of 2, pi fourths. And that's what we're going to do for a lot of our lesson today, is just convert back and forth between rectangular and polar coordinates. Oh, by the way that you describe, you need to listen carefully to this. The way that you describe the location of a point on a polar coordinate system doesn't need to be unique. Can anybody think of a different way to describe the location of point A? We can just add 2 pi to the angle. Do you guys hear that? So what if it was 3 comma, let's see, 3 pi fourths plus 2 pi, that's going to be 11 pi fourths. What if I asked you to graph this point instead of that point? Wouldn't it be the same exact point? So the coordinate location of a point on the polar plane doesn't have to be unique. You can have coterminal angles.
Negative 3, negative pi fourths.
That would work as well, yeah. Yep, that's good. Okay, so let's talk about converting. Converting between systems, coordinate systems. And rather than me just showing you or telling you what the conversion is, let's take a look at that point we were just talking about, because you guys actually converted that point pretty quickly, and I want you to realize how you did it. So in rectangular form, that was the point 2, 2. And then in polar form, that was the point 2 squared roots of 2, pi fourths. So let's be smart about this. Let's see if we can come up with some formulas that'll help us convert back and forth between the two. Yeah. Exactly. Very good. Did you guys hear that? To come up with this value of r, didn't we just use the Pythagorean theorem? Where this distance right here represents x, and this distance right here represents y. So that's one of the formulas. R squared equals x squared plus y squared. Good. So that's how we find r. Now, if all we knew were x and y, how would we find theta? Let's talk about that. How would we find the angle if all we knew was the rectangular coordinate? Let's say that we knew the point was 2, 2. How would we find the angle? Think about right triangle trigonometry. Tangent. Is that what you're going to say? Tangent. Okay. Tangent of theta. What would be the definition of the tangent of theta? Y over x. Assuming that x does not equal 0. So, I want you to put a box around these two formulas here. This is how you change from rectangular. This only works if you're going from rectangular to coordinates. So I want you to put rectangular to polar. Rectangular to polar. We have to come up with two more formulas, though, that will work if we're already in polar form and we want to go to rectangular form. So let's say now that we knew r and we knew theta. So we didn't know that this was the point 2, 2. Let's say that we knew this was the point 2 square roots of 2, pi fourths. So we knew theta and we knew r. How are we going to find out this value here? Look at the picture, you guys. If I want to find out this side of the right triangle and I know an angle and the hypotenuse, what side is this in relation to the angle? Opposite, and we know the hypotenuse. We know opposite, hypotenuse. That would be sine. Now, what side is this really in rectangular form where I had this question mark? Would this be x or y right here?
Y.
This would be y. So do you guys agree? I don't want you to write this in the box yet because we're going to have to change it. Would you agree that the sine of theta is equal to y over r? Would you agree with that? So then what is y equal? Exactly. That's one of your conversions. Y is equal to r times the sine of theta. That's if you're going from polar to rectangular. Y is equal to r sine theta. But what if we wanted x and not y? So x is down here. Cosine theta is equal to x over r, so therefore x is equal to r times the cosine of theta. So these are the formulas you would use to convert back and forth between forms. So here's example 2. Find the rectangular form of the points. So here's part A. And let's do the point 4, 2 pi thirds. It's important to recognize what form it's in. If you were just to look at this point and I didn't tell you the directions, if you were just to look at this point and I didn't tell you whether it was polar or rectangular, what would you think the form of that point is? It's probably polar because it has an angle measure there at the end. So this would be r and this would be theta. So if we're going from polar to rectangular, we want these conversion factors right here. So y is equal to r times the sine of theta. That means that y is equal to 4 times the sine of 2 pi over 3. So on the unit circle, let's take a look at the unit circle. 2 pi over 3, right here. The sine of 2 pi over 3 is square root of 3 over 2. So y is equal to 4 times the square root of 3 over 2. Which is, oh, by the way, this is something you always should do before even starting. I know that in polar form there aren't really 4 quadrants, but if you thought about this polar axis being broken up into 4 quadrants like this, where would this point be? 4 comma 2 pi thirds. It would be in quadrant 2. So you better make sure that whatever point you come up with in rectangular form is also in quadrant 2. Does that make sense? Otherwise you're going to be way off. So x is equal to r cosine theta. So that means x is equal to 4. And then if you go back to the unit circle, at 2 pi thirds, cosine is negative 1/2. So x equals 4 times negative 1/2, which is a negative 2. So in rectangular form, the point becomes negative 2 comma 2 square roots of 3. Now just think for a second, does this make sense? Where is this point in the rectangular plane? This is in quadrant 2, just like this one is in quadrant 2. Try this one on your own. Here's part B. I want you to work on it for a second. So that's in polar form. Take a minute and that is a 7. Take a minute and convert that into rectangular form. So x is equal to r times the cosine of 7 pi fourths, and y is equal to r times the sine of 7 pi fourths. So, to the unit circle. 7 pi fourths. The cosine would be square root 2 over 2, and the sine would be negative square root 2 over 2. So this equals 3 times square root 2 over 2. Y would be 3 times negative square root 2 over 2. Well, these don't simplify too nicely, do they? Oh well. So we have 3 square roots of 2 over 2, comma. Negative 3 square roots of 2. That what you guys got? Let's go the other direction now. Let's go to example 3. I'll have you guys do this on your own rather than me showing you. I think you guys can figure this out. Now you're going to convert to polar form. Convert to polar form. So there is a point that's in rectangular form. Oh, hold on a sec. just to follow the directions of your book would say this in parentheses. R, well, how do they state it exactly? R needs to be greater than 0. And they would also say that theta needs between 0 and 2 pi. That's how they would say that. Well, let's actually do this one together. R squared is x squared plus y squared. So, three squared, so 3 squared plus negative 3 squared. It is just basic arithmetic, but you have to know what you're doing. 3 squared, so 3 squared? What is that? 27, yeah. 27. You square both of these terms inside the parentheses. 3 squared is 9. Square 3 squared is just 3, and 9 times 3 is 27. So this is 27 plus 9. So r squared. Well, this turned out nice. Wow, we got lucky. So r equals 6. Now, the tangent of theta is equal to y over x. So this means tangent of theta is equal to negative 3 over 3 square roots of 3. Now, it doesn't really matter to me if you rationalize this or not, because we're just going to take the inverse tangent of it anyway. This is not going to appear as part of our answer. Does that make sense? You don't need to take the time to rationalize this, because all we're interested in is theta. How do we find theta? Inverse tangent on both sides. So you can just leave this in this form. Theta is equal to the inverse tangent of negative 3 over 3 square roots of 3, but you can't just blindly trust your calculator on some of these problems. I'll explain what I mean here in just a second. So what mode am I in? I'm actually going to change this to degree mode. In this case, when you're converting from rectangular to polar, it would be easier for you to be in degree mode. So, inverse tangent, oh mama, negative 3 divided by 3 square roots of 3. So the calculator isn't incorrect, it's just not necessarily in the interval that the homework wants it to be in. Theta needs to be between 0 and 2 pi. This is negative 30. So, what's the problem here? Not only does it need to be in, you're right, it needs to be in radians, but negative 30 is less than 0. So just go the other way. Negative 30 is going clockwise. Just go counterclockwise around the circle. Negative 30 going clockwise is the same as what going counterclockwise? 330, right? So theta, you just add 360, yeah. Theta is 330 degrees. Technically, they do want it to be in radians here, like it says. So you can either convert it by hand or just check out your unit circle. That should be on your unit circle somewhere. 330 degrees, what are you? 11 pi over 6. Well, that was an easy conversion. So that's the same as 11 pi over 6. So the point in polar coordinates becomes 6 comma 11 pi over 6. This is actually really good practice, especially this example right here, going from rectangular to polar, because this is exactly the same process you guys are going to do when you're finding the direction and magnitude of a vector. These same formulas work with vectors when you're going from rectangular to polar. Let's do one more. This one's going to be Let's see. It's going to be something, I'll just say that. Let's do negative square root of 6 comma negative square root of 2. Same directions, r has to be positive. And by the way, you guys, if we're using this conversion formula, take a look at this. If we're using this conversion formula, won't r always be positive anyway? So we'll never really have to worry about that. But it's theta that you have to sometimes be clever about. Luckily for you, most of you guys are pretty clever. Oh man. Let me back this up the way down here. Part B. There we go. What quadrant are we in, by the way? Third quadrant. Alright, so r squared is negative square root of 6 squared plus negative square root of 2 squared. So what is that? 8. Yep. R squared equals 8, so r is equal to 2 square roots of 2. Here's what I was saying just a second ago, that you cannot just blindly trust your calculator. And I'm going to say this 3 or 4 times, and even though I'm going to say it 3 or 4 times, a lot of you are going to screw this up on the test because you don't listen when I say it 3 or 4 times. Listen carefully. Here's the issue. If you just follow the formula, you're going to get negative square root of 2, whoa, negative square root of 2 over negative square root of 6, which is negative divided by negative is positive, right? So tangent of theta is the square root of 2 over the square root of 6. If we just took the inverse tangent of this, what do we get? Let's see, inverse tangent of square root of 2 divided by the square root of 6. All right, 30 degrees. We're good to go, right? The direction of this is 30 degrees. It's not. Okay? We said right at the outset of this problem that this point needs to be in which quadrant? The third quadrant. But 30 degrees is not in the third quadrant. Did the calculator mess up? Did we mess up? We didn't mess up. Here's the problem, you guys, listening carefully. This calculator only acts as a function. One input provides one output. Do you remember how we had to define tangent in order to use inverse? Negative pi halves to pi halves. What quadrant is that in? Negative pi halves to positive pi halves. That's quadrants 1 and 4. The only answers you will ever get from your calculator for inverse tangent are quadrants 1 and 4. So how then can we get an angle that's in the third quadrant? You have to add 180. Okay? So here, theta does really equal 30 degrees, but that's not the theta we want. The theta we want is in the third quadrant. That means this is just a reference angle. 30 degrees is a reference angle for 210 degrees in the third quadrant. So the theta angle that we really need is 210 degrees. So the point in polar form is 2 square roots of 2, comma, well, 210 degrees. We actually want this in radians. So yeah, 210, that's 7 pi 6, exactly. 7 pi over 6. There you go. Now we're This is where it gets fun. We've been doing these with coordinate points. We now have to do this with equations. Like the equation of a line in rectangular form is y equals mx plus b, correct? We need to convert similar to rectangular form between lines and circles and ellipses and things like that. So now we're doing equation, which is not quite as easy. So here we go. But you know what? It uses the same formulas, which is nice. Those same conversion formulas. So here's example, what is this? Example 4. Express the equation in rectangular. And we're going to have a couple of parts here. Part A. Here's an equation. R equals 5 times the secant of theta. Now, other than the fact that I told you this was already in polar form and we need to go to rectangular form, if you were just to look at this equation, how would you know it's already in polar form? Because it has an r and has a theta. There are no x's and y's. Rectangular form has to have x's and y's. Suggestions. That's what I would do. Say that again.
Change secant.
Into good. That's what I would do. Because if you notice, the reason for doing that, if in case, well, why the heck would we do that? In case you were wondering, our conversion formulas only deal with sines and cosines, right? If we have something in terms of secants or cosecants or anything else funky, we probably ought to not use them. So let's change that. This equation now becomes r equals 5 times 1 over. Is that what you were talking about doing, Dan? Okay, just so I understood you right. Okay. These, much like, here's the difficult thing, you guys. The arithmetic involved is not difficult. It's the ingenuity involved. Sometimes you have to be creative, much like with your identities. Here's what I'm talking about. Please listen to this and try to pay full attention to what's going on here, not anything else. In order to go from polar form to rectangular form, we have to have this kind of a thing, r sine theta or r cosine theta, because that's where we're going to get x and y. You guys listening? We need to have something that says r sine theta or r cosine theta, right? Well, here's what we have in this equation. We have an r, but we don't have like an r cosine theta or an r sine theta. How can we remedy that? What if we multiplied this, is that what you were saying, Maddie?
Yeah.
What if we multiplied this by cosine theta and this by cosine theta? Why in the heck do we want to do that? It actually does two things. Not only does it get rid of this funky trig expression over here, but over here, what do we get? R cosine theta. Why is that so important to get R cosine theta? That tells us what x equals. So that's exactly what we would want to do here. So now we have the equation R cosine theta is equal to 5. But what is r cosine theta? X. So we have x is equal to 5, and that is the equation. That's in rectangular form. How do we know it's in rectangular form? Because it's in terms of either x or y, and there's no more r, there's no more theta. What is that, by the way, x equals 5? It's a vertical line, yeah. Because on a vertical line, all the coordinates are going to be x equals 5 on that vertical line.
But all you have to do is from one.
There is no y in this one. In rectangular form, you don't have to have both x and y. Sometimes you have one or the other. Let's try another one. Part B. That's the good and the bad thing about this is you don't do the same thing every time. Step 1, step 2, step 3. It's more a matter of creativity, like when you were doing your identities. Sometimes things work great one way, but they don't work great in another problem. So here we go. R equals 2 times the sine of theta. Now, a moment ago I mentioned it's really nice if we can get like an r sine theta or an r cosine expression, r cosine theta. It would also be really, really good if we could have an r squared in there somewhere. What if we did have an r squared? What is r squared equal to? X squared plus y squared. So there's another hint. If we can get an r squared in our equation, then we can just change that to x squared plus y squared. So with the ooh boy, where did we go? Hold on now. Here we are. So with this equation, I mean, we could try the same thing we did last time. If we multiplied both sides by sine, then yeah, we would have an r sine over here, but then over here, what would we have? A sine squared, and that's just going to get really difficult to get rid of because that's 1 minus cosine squared. But then we have a cosine squared, and that's really hard to get rid of. So it really wouldn't be the best thing to multiply both sides by sine in this case. Now you can perform some operations to this to change the form of it, but the thing is you can only perform operations that are 100% reversible. And here's what I'm talking about. A lot of students will recommend, well, hey, let's just square both sides. And I understand why that seems like such a good idea. Why does that seem like such a good idea? Because now we have r squared. But the problem is squaring both sides isn't 100% reversible. Because how would you reverse squaring? Square rooting. And when you square root something, you get plus or minus, which really gives you two outputs. Do you understand what I'm talking about? Squaring both sides isn't 100% reversible, because when you go backwards, you end up with two outputs. So we're not going to square both sides, but I'm just telling you guys, we do want to have an r squared. That's our task. I'm going to leave it up to you for just a second here to think about it. How in the world can we get an r squared if we can't square both sides? Multiply both sides by r. Is that reversible? Is it 100% reversible? How would you get rid of multiplying both sides by r? Just dividing by r, and then you'd end up with the same thing. So that's reversible. This is actually accomplishing two very important things. Not only do we have r squared on the left side, but what do we now have over here? R sine theta. Exactly. So what we have now is r squared equals 2 times r sine theta. And r squared is just x squared plus y squared. And r sine theta? What's r sine theta? Well, come on! It's just y, so this turns into 2y. Now check out what we have. Are there any more r's or any more thetas? No. So technically speaking, that is rectangular form, but I'm not going to let you leave it in that form because we don't know what the heck this is. What is this? Is it a straight line? Let's decide what it isn't, I guess. Is this a straight line? No, it's not a straight line because we have, is it a parabola?
No.
Because it has x and y both being squared. If one of them was being squared, it would just be a parabola. It's either a circle. Remember the conic section? It's been a couple of months. It could be an ellipse or it could be a hyperbola. So we actually need to figure out exactly which one this is. That means we got to complete the square. You guys were waiting for this, weren't you? Subtract the 2y over. I know it's been a while. This was way back in our 1050 section of this course, but we're going to have to complete the square to figure out what this is. So we're only going to complete the square on y, because that's the one that has two different terms. So we have y squared minus 2y, and then I got a blank spot here. What completes the square for this blank spot? Plus 1. How'd you know that, by the way? Divide b in half and then square it. This should all sound remotely familiar. We spend a little bit of time on it. But we just unbalance the equation. We put a plus 1 over here. You can't do that without doing what? Adding it to the other side. So now we have x squared plus y minus 1 squared equals 1. All right, what is that? How quickly we forget. It's a circle. Now, technically, it is also an ellipse because a circle is just an ellipse. It's a special kind of ellipse. But it is a circle because if we considered what... wouldn't this look more like the equation of an ellipse if it has denominators? But if a and b are exactly the same, it's just a circle. Just a circle. How's the conference? 5 seconds.
That's why I'm texting.
Have I ever gotten a ticket? Gotten like 40.
He's kind of a crazy driver.
Like the running red lights.
I get a lot of tickets.
What if you would hit me? What if you would hit my car by running that red light?
I'm smart about it. I don't just run red lights. I check to see who's
No,
coming.
you didn't. I was
And then I
going.
go.
You went right through it.
You were in a teeny car, and I was in an Astro van, and you're like,
If there's a red light and there's nobody coming the other way, then the red light's useless.
I was going the other way.
But you hadn't started yet.
I was about to, but then I stopped.
I'm
because
older,
saw
so I have the right of way.
I was so fast.
I have the right of way.
You would have ruined your swim team.
All right, let's try another one.
Wait.
I've probably spent over $3,000 or $4,000 on tickets. That sucks.
3 or 4,000.
Mostly for speeding.
But if you stop breaking the
I
law,
was going 10 over once, and I threw that my door.
Do you remember that one time we raced and I won? And I won.
You beat me off the line with your van?
Yeah. It was after something.
Oh, we were over right in front of Westlake, right? Yeah, I remember that.
It was like, what was he?
You get it from speeding? Is that why you
Mostly. But since I started listening to classical music, the speeding has gone way down. Gone way down.
Or are you listening to the chorus right now?
X96. I turned on the classical music and I've calmed down big time. I don't have road rage anymore either. I was a big road rager. Okay. R equals 2R plus 2R cosine theta. Say again. From here? Okay. We could try that. So we have, is this what you were talking about doing? Okay. We're going to probably have to do a similar thing that we did on the problem above, because we really, really want to try to have an R squared here. Say again?
Like 2R plus 2x.
Wait, I heard two different things. Let's go here, and I don't think you said the same thing.
You have like 2R plus 2x.
2R, wait, say that, 2R plus
Like R cosine x is x.
here.
Yeah.
So you're saying not do this?
Yeah.
That might actually work out a little better, but let's, Parker, what were you saying?
maybe we should factor 2 out so we have R plus I plus theta.
Okay. Let I'm actually going to erase this because that might have made things a little bit harder. The reason I was going to erase that is, you see what we have right here right off the bat? Is this what you were talking about? We already have an r cosine theta right there. So straight away, what could we do with that? We can turn that into x, right? We can turn that into x. So let's do that straight away. Let's do r equals 2r plus 2x. Oh, wait a minute. Oh. Shoot, this sucks. Today's already ruined. This just ruined today. It's done for. I wrote down the problem wrong. It's not worth fixing. Just give up. No, let's fix it. Erase! Dang it. Don't you hate when that happens? You know the problem is I skipped breakfast again.
Oh my gosh.
I should never do that. This is what it should have been. Ooh, there was an R right here to begin with. I was getting a little overzealous. There shouldn't have been an R right there to begin with. Dang it. What did we do first on this problem here on part B? Multiplied by r. The reason for that is this r would have turned into an x squared plus y squared. And if we multiply this side by r, not only does that get an r squared, but what does this get? It'd be an r cosine theta. So let's multiply both sides by an r. So we're going to have r squared equals 2r squared plus 2r cosine theta. Okay, now we're getting somewhere. Say again? Did you have an idea?
Yeah, but not really. But we did exactly what we did before with the r cosine theta.
Yeah. Take the r cosine theta, turn that into x, and then what about the r squareds? Yeah. Let's just do the straight conversion right now. This is going to be x squared plus y squared. This is going to be 2 of those x squareds plus y squared plus 2x. Now you got to be careful to put this x squared plus y squared in parentheses because it's got to be, the whole thing's got to be multiplied by 2. So let's see what we have now. We have x squared plus y squared equals 2x squared plus 2y squared plus 2x. Now what were you saying, Brady?
Get everything on one side.
So what would you do? How would you do that?
Like subtract x squared, y squared from the outside.
Okay. So we're going to have 0 equals x squared plus y squared plus 2x.
And then we do on the square. Complete the square.
Now we got to complete the square again. Yeah? But let me rearrange this. I want to put this y squared and the 2x. I'm going to put the 2x here and the y squared over there. Just get the x's together. So what completes the square? We have x squared plus 2x. We're going to have a plus some kind of a number that completes the square. I think it's just the same one as last time. What did we do last time? Yep, plus 1. This time it's going to be a plus 1. So we're going to have 0 equals x squared plus 2x. And we have to add that plus 1 to complete the square on x. But then add 1 to the other side to balance out the equation. We have 1 equals quantity x plus 1 squared plus y squared. Another circle. Let's just do one more quick example before the bell rings of going the other direction. We've been going from polar to rectangular. Let's go from rectangular to polar. This will be example 5, last one here. Let's take the equation. Excuse me. And the directions are to convert to polar.
Okay.
Now you guys, this would be really, really, really easy if this were x squared plus y squared. Why would it be so easy if this were a plus sign? That would just be r squared. R squared equals 1. But dang it, this one isn't quite as easy.
You can change some of the equations we use to replace what we have in the equation.
Okay, what do you mean?
Like the equation that says r squared equals x squared plus y squared. You can change that to x squared equals r squared minus y squared.
True, you could. You absolutely. So let me see if I can go back here. So you're talking about rearranging this one?
Yeah.
Yeah, that wouldn't be a terrible idea, but the one issue with that is we would get the r squared in there, but then we would also end up with another rectangular part, like an x or a y, and those are the ones we're trying to get rid of. Does that make sense?
Yeah.
When we're making a conversion, we want to take out all the x's and y's and just have r's and thetas.
So you want to use the other equation, the y and x.
So we probably ought to stick to these. So x is equal to r cosine theta. What is x squared equal to? Yeah.
Can you just subtract the x squared out of the y squared and back down to negative 1?
What's that?
If you move them both to the other side, you factor out of 1.
Move the x and the y to the other side?
Yeah.
So you'd have 1 minus x squared plus y squared equals 0.
Yeah.
If we factor out our negative 1,
Or could we?
we have x squared and we still have that minus y squared. That's not a bad idea though. See, these are good ideas to have and try and see if it works. It's not a bad idea.
Did you put like the y times cosine and just square that?
That's probably what we're gonna have to do. Do you guys hear that? Isn't x equal to r cosine theta? So then, what is x squared equal to? R cosine theta squared. Is that what you were saying? That's what we're gonna have to do here. This is going to be r cosine theta squared minus. Now, what's y equal to? R sine theta squared, and that equals 1. Now let's simplify this. This is going to be r squared cosine squared theta minus r squared sine squared theta. Factor out the r squared. We have cosine squared theta minus sine squared theta equals 1. Yeah, this is getting pretty deep. Does anybody recognize this? You should if you took the test on Friday and did pretty well. This, it's a double angle identity. This is cosine of 2 theta. So this is r squared cosine 2 theta is equal to 1.
Polar, huh?
Yeah, these get a little tricky.
I don't usually.
So that's how we would stop.
Did you get any
I didn't even know that. I didn't even know
Dang it! Why is that?
Dang it. Oh, I was down in the office. What, you expecting somebody else?
Yeah.